So here we go. This is AP Dual Credit Psychology, Unit 2, Lecture 5. We are covering the endocrine system and also how we study the brain. Um, and this should be the fifth lecture of this unit. You should have recently wrapped up your labeling of the brain and neuron quiz. And now we're going to take a look at the endocrine system. We've looked at the nervous system, we've looked at neurotransmitters, that almost instantaneous communication. So now we're going to look at the endocrine system, which communicates through hormones, which takes a little bit longer. Then we're going to take a look at studying the brain, which is a game changer in psychology, because up until the 70s into the 80s in modern medicine, a lot of the beliefs of what made man tick, reward, punishment, subconscious, whatever, it was based on philosophical ideas. Now we actually have science which can show the brain in action as it's being rewarded, as it's being punished, or anything else, and what part of the brain is in control of what. So we're going to take a look at that as well as we go through. So let's start with the endocrine system. This is, again, the nervous system is all the neurons. It's an instant message. When I pick up this highlighter, the brain, the motor neurons, sends efferent neurons exiting the brain, motor neurons, to pick this up. And then the sensory neurons, the afferent neurons, which are coming back to my brain, can feel it. All right, so me holding this marker, that's an action. It's an action I can do almost instantaneous, faster than I can come up forward. So that's, but when I pick up this marker, it has nothing to do with my foot. It has nothing to do with this shoulder over here. It has nothing to do with my ear. It has nothing to do with my chest. It's a message. It's between my hand and my brain and my brain and my hand. It's very isolated. So the communication is quick and it's very individualistic. That is the nervous system that we've talked about. It's rapid and it's isolated. Endocrine system a little bit different because the endocrine system is communicating throughout the body, and it's done with hormones. And in order for a hormone to communicate with other parts of the body, it's got to be sent through the bloodstream. And to be sent through the bloodstream means it's got to go through the whole body. When we're checking the blood sugar, we got to check the whole body. When the stomach is using leptin to send to the hypothalamus, hey, I'm full, stop eating, it's got to work its way through the whole blood system before it gets up there. As we said before, it takes about 20 minutes for that conversation to get up there and back. So the nervous system, it's automatic, or not just automatic, but it's quick and it's isolated. But the endocrine system is long-winded, and it just sort of takes forever to do. It's a difference between an instant message and putting something on social media. Social media, where everybody can see it, that's the endocrine system. Instant messages between you and that person, unless they cut it and paste it and show it to other people to blackmail you. But it should be isolated between two folks. And they're the only two folks who are involved. So again, me picking up this marker is between my brain and my hand using this. That's the nervous system. That's neurons doing that. But the endocrine system using hormones goes throughout the body. So we're going to take a look at some different parts of the endocrine system here that we think are important. And again, the communication is happening through hormones. All right, very, very important that you sort of understand that, because they're going through the bloodstream and it's a slower process and it involves all of the body. Now, excuse me, one of these hormones that is sent through in times of stress is adrenaline. The adrenal glands that we have are located right here, like the little beanies on top of our kidneys. And that is what produces adrenaline, and that sends that extra energy, that extra power through the bloodstream. And again, if it's just, I'm nervous, I need energy to pick this up. I need to pick this up. So I need that extra strength to pick this up. But that extra strength is also given to my legs. That extra strength is also taking blood away from my brain. That extra strength is, I can't isolate it in the way that I can something sent through the nervous system. So when I secrete these hormones, and then the epinephrine is also sent through my nervous system, once the stress is done, the adrenaline sort of sits there. If somebody cuts me off in traffic, and I go through the fight or flight response of, oh my God, somebody cut me off, that's dangerous, and everything else, and you know, and then your heart starts to beat, and you're pumping the adrenaline along, and everything else, and then that person's gone. You still have that, excitement in your body because it takes a while to get the adrenaline, but then once you get the adrenaline, it takes a while to let it go. Whereas once I drop this marker, it's over between my brain and my hand. But when I get all this adrenaline to fight whatever I got to fight in the fight or flight situation to resist the stress, and even when the stress is over, the person cut me off, they're gone, they've gone to their neighborhood, I'm still sort of feeling that whatever. You get into the argument with whoever, and the argument's over, and you're still like, because that adrenaline is still in your body, which is why a lot of people would recommend that when you get to the end of your day, especially a stressful day, you go to the gym. And the reason you go to the gym is you want to use up that adrenaline and everything else and get it out of your system, because we'll talk about this when we get to stress. What happens is my body's reaction, my physical reaction to stress and how I deal with stress and all this extra adrenaline, it just builds this toxic environment. And then what happens is my reaction to stress, my physical reaction to stress is more damaging than anything that's causing me stress. I'm not going to get eaten by a lion or anything, but heart disease is the #1 killer in America because I'm spending all this time again, this adrenaline and pushing the blood through, and then my arteries are getting smaller and smaller. That's what kills me. All right. Oh, one other thing I have to point out here is the pituitary gland. And the pituitary gland is very important because the pituitary gland is kind of in charge of the endocrine system and the wants and the needs and everything else. Remember, my hypothalamus is right here. My hypothalamus talks to my pituitary gland. So my pituitary gland, which is this little pea-shaped, pea-sized thing right in the side of our brain there, that's actually the guy who is in charge of everything in the endocrine system, which has to do with growth, blood pressure, water regulation, this homeostasis, the temperature balance. You know, if my blood is feeling too warm, I'm going to need to get some air conditioning and cool down. If my blood is feeling too cold, I need to put on a sweater. So it's trying to measure the homeostasis throughout the rest of my body. Checking my blood sugars, my metabolism, okay, for people who are pregnant, lactation, all these other things to be able to take care of the little fetus inside of you. All these things are regulated by the pituitary gland. So a lot of times when people struggle with blood pressure or have these growth spurts that are out of control compared to the rest of their family, sometimes the issue is within the pituitary gland. So again, the job of the pituitary gland is to talk to the hypothalamus. So it's hanging off there. It talks to the hypothalamus. So the hypothalamus, so the pituitary gland asks the glands, hey, how are you feeling? Are you warm enough? So it sends hormones around and it checks the blood temperature and everything else. And then when the blood temperature comes back as being okay, or as let's say it's a little cold in the brain and the hypothalamus, we tell them to put on a sweater. Okay, now how are you feeling? Let's go around and let's go back to it. And this constant communication where the pituitary gland is sort of the translator to the rest of the endocrine system from the hypothalamus. But again, when I'm telling my hypothalamus to eat, a lot of times I'm telling it to eat based on what I was feeling 20 minutes ago. So if I'm telling it to eat and I'm just sitting there munching on chips for half an hour, I could have been full 20 minutes ago, yet I'm still putting these chips in because it takes a while for me to sort of go through the rest of my body and check the blood sugar and everything else. So again, it takes a little while. That's the main thing about the endocrine system communicating through hormones. It takes a little while to work our way through that, whereas the brain and the hypothalamus, it's instantaneous. Go to the kitchen, go get some food, go get a drink, put on a sweater, very, very quick, lightning fast compared to the endocrine system. Now, other parts of the endocrine system, which I'm not that overtly concerned with, but just so you're aware, the thyroid, which produces thyroxine, this stimulates chemical reactions to all the tissues. If my thyroid is overactive, I'll feel anxiety. If it's underactive, I'll feel lethargic. And sometimes people will have what is called a hyperactive thyroid, and where their adrenaline just sort of keeps going and going and going because it has a butterfly effect, and it sort of affects all these other things where you sometimes can't calm down because your thyroid is so sort of overactive in these situations. Again, they work to inform functions of the brain, the eyes, the heart, intestines, hair, skin, so they can have an impact on the digestive system and all these other things. So the thyroid can be pretty important. Now, the sex glands, again, I don't want to turn this into a health class, but It comes down to testosterone and estrogen being the two big communicators of those hormones. The testes produce sperm, reproduction. Androgen and testosterone help the growth of the muscles. Male characteristics in adolescence, going to drop your voice if you are a guy. Women do have levels of testosterone. They just tend to have less than men. On average, men have 7 to 8 times more testosterone than females have, which is why men tend to be a little bit more aggressive because testosterone is also very much linked to aggression. And again, testosterone affects us all differently. As far as guys go, will help produce hair on your body. I have a very, very low voice, but if I try to grow a beard, I look like a radiation victim with patches everywhere. Your muscular development, a lot of testosterone is going to give you broader shoulders. Your muscles are going to be a little bit thicker, which is why some people will take, artificial supplements for things like that as well. But that's testosterone, which tends to be greater in men than what it is in women. On the other side of the equation, women with their ovaries for reproduction, but it also produces estrogen and progesterone. This helps regulate the reproductive cycle, but it also has effects on other things. The lack of hair, the way that fat is distributed on the body, and all these other things. And that's why when you have somebody who's going through what is referred to as a transition, somebody who is born with male characteristics but identifies with being female or vice versa, one of the things that they'll do when they're doing this transition is they'll start with hormone therapy. And if you have a woman who's transitioning to male, she'll start to get shots of testosterone. And when you have someone who was born male transitioning to female, they'll get extra shots of estrogen. And what it does, again, it changes the way that your body is shaped. Women who naturally put fat on their thighs and hips will suddenly transition that fat to go more around the trunk like a man, and vice versa. Women may start to beard and may start to have a little bit more breast development, things like that. And again, when it comes to the hormones and the reproduction, the estrogen is at a very high level with women from the 20s to the 30s and 40s. And there's this extreme drop off right here, which is called menopause. And menopause for women is sort of a reverse puberty, where the hormones are being produced at a different rate and your body has to adjust. My wife's going through it now, and it's really sort of funny. Well, not funny for her, but for me, it's kind of hilarious. But for guys, the testosterone level that drops from our 20s drops, but it's a much more casual drop that happens. It's not this dramatic thing. But women, the fact that they can't have kids for the most part once they hit their late 30s, early 40s, there's less of a need for the estrogen, whereas men can reproduce for a longer time. Oh, and one other thing, I have to point out that every time I see a set of ovaries, it looks like the Texas Longhorn. Sorry, I'm immature. So again, there we are, another little graphic there on the endocrine system as a whole. Now, studying the brain. We talked about the split brain, where you take the corpus callosum and you purposely cut it. A lesion in a brain, any sort of lesion in the brain, is the part of the brain that is destroyed. Sometimes it's naturally destroyed, where you see multiple sclerosis, where it's very, very white here. That's where you have those axons not really protected by the myelin sheath. Here you can see a stroke just sort of blew out this part of the brain and its activity there. So there's destruction. Or sometimes what happens is a lesion is done medically on a brain because of someone's having seizures. And the reason you're having seizures, the neurotransmitter is just firing. It's going on a loop again and again and again and again. So someone may have, if they have a seizure, they may like snip a little wiring there to stop that constant cycling. But that's a last resort thing, because once you destroy part of the brain, you can't just reproduce it. You can rewire the brain to work around it and suddenly have, someone over here with a stroke, you can retrain them where this part takes over for this part, but it's hard to repair a part of the brain that is destroyed. And again, I told you the story of this little girl who had a lobotomy, but since she had a very young, this side of the brain, this doesn't recreate, but this side of the brain sort of took over a lot of the functions of that side of the brain. So when we're studying the brain, there's a lot of different ways we can do it. One way to do it is what's called an EEG, which is an electrograph. this is where you put little wires on top of the brain here. And what they're able to do is they're able to listen to a neurotransmitter. And these microphones can get it down to a single neuron. And that single neuron, the little sort of zzz that they're making, that's the activity of the neuron. That's how fast it's firing, going across the synapse, being picked up by others. And you can use that as a fingerprint to see how the brain is working. And we'll talk about sleep down the road, but you can see this example of reading a neuron. When somebody is awake, it's very, very, very quick sort of a signal here. You're relaxed and drowsy, and it becomes a little bit higher and a little bit slower. Stage 1 sleep, you start to have a little bit of a bigger gap, a little bit higher. Stage 2, the gaps become even bigger, becomes a little bit higher. It can come back to alert real quick. But there's these bigger gaps. In stage 3, we start to have these delta waves. In stage 4, the neuron's really slow, big gaps, completely asleep, able to re-energize because the brain is working so slow. But then we get into REM sleep, and REM sleep is like we're awake, because when we're dreaming, we got to come up with plot and dialogue and characters and all that crap, which is very, very, very active in our brain, which is why we only dream for 10 to 15 minutes at a time. Because if we dreamt all night, we'd never get any rest. We want to be in this stage 4, this delta wave, where time seems to go a little bit faster. If you've ever fallen asleep and woken up and you're like, oh my God, 2 hours just passed by. You got a lot of delta sleep. You got a lot of delta sleep. If you wake up, it feels like you just went to sleep, but it's been a few hours. That's the good money sleep. And that can all be measured in an EEG. So a lot of times when someone has a sleep study done, they'll put the EEG on them. Here again, this is an example of an EEG. You'll notice this communication. This is somebody before a seizure. This is somebody during a seizure. And notice that during the seizure, the activity is much, much higher and it's much faster. Focus on this yellow right here compared to that yellow. Very, very steady, very, very, it's active, but it's not off the charts. This thing is kind of off the charts. And then the EEG after the seizure very much looks like this one over here. So this is able to measure when you have this sort of overwhelming electrical signals versus these normal electrical signals, where you can basically graph somebody having a seizure. This is another example of an EEG. As you get deeper sleep, the waves become bigger in stage 4, and then you get back up into the stage 1, stage 2, or the REM sleep, it gets a little bit shorter. Big waves. Then as we're in the deep sleep, but then we get up into the dreams, and it's very, very short waves. So you can sort of see that through an EEG. We'll talk about that more when we get to sleep. Not when we get to sleep, but when we cover sleep. A CAT scan. A CAT scan is what's known as computer axial tomography. We call it a CAT scan because it's easier. And what this basically does is it slices the brain. If you would. So it's taking a bunch of horizontal pictures. And you can see that this is someone who, that's their eyeballs, that's their nose. So this is the base of the brain, a little bit higher, a little bit higher, a little bit higher, until we get all the way up to the tippy top of the brain right there. So this is the top of the brain working our way down, working our way down, working our way down. And what this does is it gives you all of these little slices of the brain, these two-dimensional pictures, which allow you to see, is there an irregularity in the brain? Is there a discoloration, where there's a bunch of white where the brain was destroyed or whatever? So a lot of times people will have a CAT scan done, especially if you're in a sport and they think you had a concussion and they want to see if there's like a pressure against the skull or anything else like that. That's where a CAT scan would get done. Here's some examples of a CAT scan, sort of working your way up here. You can take a series of CAT scans, put them together, make a 3D image right there. And that's sort of how it works. It goes around the brain, and it gives you all of these different slices of the brain working up. Now, a little bit more advanced than that is a PET scan. And what a PET scan does is it gives you a visualization of the brain, but rather than just take a picture of it, it's showing you the activity in it. So the brighter the colors that you have, the more neurotransmitters are going off, so the more active. You look at this PET scan over here, somebody who sees words, their occipital lobe firing on all cylinders here. And then when they hear words, their temporal lobe is a little bit more active. You know, this is a resting brain. This is somebody who's walking, so they're using their cerebellum, seeing, hearing, thinking. The frontal lobe starts to come in, remembering. I'm using a little bit of my temporal lobe back here, trying to visualize what I saw. So you can see different parts of the brain that are active. And again, the more active your brain is, the redder the color is going to be. The less active, the darker the color is going to be. Here you see a normally active brain with a lot of activity. This is someone who's depressed, less activity, overactive amygdala, but the frontal lobe really isn't active. The normal brain, you got a lot of frontal lobe activity, but the murderer who doesn't have as much empathy, not as much frontal lobe. Normal controlled person here, obsessive compulsive, your frontal lobe is overactive all the time. How does this impact other people? You're always worried about that. Again, normal person, Alzheimer's, having trouble finding those memories. They're there, I just can't find them. And as you become older, you'll notice the brain becomes active. This is the first year of life. 1 month, 3 months, 6 months, 12 months, the brain starts to become very active, whereas when you're a little baby, it's not a lot going on there. Similar to the CAT scan, you got an MRI. Now, where a CAT scan is 2 dimensions, it just sort of slices up, slices up, slices up, and gives you all those hemispheres. A MRI gives you a 3D picture of something. So you can sort of work your way around it. You just don't have to go up the levels. You can look around, so you can see things like here's a tumor, here's a really great MRI where you can see the cerebellum and the corpus callosum and the thalamus and the pons and the medulla. You can sort of see all these different parts of the brain in actions. Again, here's an MRI giving you the 3D. This is going from the bottom up to the top. This is going from the left to the right. This is going from the front to the back. So it gives you all of these sort of 3D images. Then if you combine that with the PET scan, you could actually combine where these activities are sort of happening in the brain. So that's an MRI. And I'm sure a lot of you guys have had MRIs on parts of your body, a shoulder, a knee, or whatever, where the doctor's trying to find what's wrong with it before they go in. So again, these are all different ways that you can study these particular parts of the brain. Just sort of a graphic there which goes over. All right, so that should wrap up Unit 2, Lecture 5 for AP and dual credit psychology.